So we're going to finish up chapter 8 talking about polarity. So again, polar, nonpolar are both two types of covalent bonds. They're sharing electrons, not equally though. And why this is important, okay, especially with the holiday seasons coming up, okay, is polarity matters. You cannot combine polar and nonpolar substances easily, okay? This is also the majority of my work for my PhD is based on the polarity of substances and how they behave at interfaces. Realistically, polarity explains why you put in a frozen turkey with all the nice polar water molecules into oil, which is a nonpolar substance. They don't react very well. They don't dissolve. And so there's more splashes, and you have this nice explosion when people try to fry turkey. So remember, for Thanksgiving, please be careful when you are, if you or your family plan on frying turkeys. You can also explain the science behind it. So that would be a fun Thanksgiving discussion. So polarity, what does it mean, and can we predict it? So we predict polarity and whether you have a polar or nonpolar bond based on electronegativity. So I briefly covered it, mentioned it a few videos ago. Okay? But electronegativity is the ability of an atom and a molecule to attract electrons to itself. So basically, it's an atom that wants the electrons to hang out with it. Okay? We've talked about the ionization and the electron affinity back in Chapter 7. Now again, Chapter 7 material has those nice trends, right? You remember all those trends? A lot of that was covered, was expected to be covered by you at home. So if you haven't reviewed your Chapter 7 material, go back and do so, because you'll see a very similar trend with electronegativity. Ionization energy, remember, measures how strongly an atom holds on to its electrons. Okay? Electron affinity measures how strongly an atom attracts additional electrons. So an electron that has high electron affinity, meaning stronger electron affinity, would like to have a strong electronegative behavior. So it wants the electrons around it. It's not going to give them up. It's going to take more electrons. So they will have a negative charge. So you're not going to see very strong electronegativity in molecules with positive charges, right? Because they gave up the electrons. So an atom with a high ionization and a very negative electron affinity will have a high electronegativity. What this looks like, if we look, is basically, once the electronegativity will tell us where the electrons want to reside the majority of the time. Okay? And you can see, again, low electron negativity with these nice, lovely cations, and as we move to an anion, negative charges, you have an increase in electronegativity, where fluorine being what we call an electron hog. The difference in electronegativity can tell us about the bond polarity. So if you have two that have a very similar bond or electronegativity, so hydrogen 2.1, carbon 2.5, that's a very low change, right? There's not a dramatic change, so it's not likely that the electrons would prefer carbon over hydrogen. But if you go from hydrogen to fluorine, you see that it goes from 2.1 to 4.1. So that's a change of 2. That's a pretty big difference. That's actually one of the larger difference if you think about the nonpolar components. Okay, so again, just nonpolar. So fluorine, being more electronegative, will take the electrons more of the time. Okay, so notice how all these values are unitless, and we're really just looking at the change in the electronegativity between the two atoms in a bond. Okay. So the most electronegative element, I just said, okay, is fluorine. So fluorine, as we get closer and closer to fluorine, it becomes more and more electronegative. So the elements around fluorine, oxygen and chlorine, are more electronegative. They are called electron hogs. They hog the electrons. They are the siblings that take the majority of the candy bar. Okay. Notice how we ignore column 8. Just like all the other trends, column 8 are noble gases. So they're not going to react very well. Okay. So in electronegativity, or looking at polarity of electronegative compounds, in a polar bond, meaning we have a charge, bonds carry a partial positive and negative charge. They're not formal, so it's not like ions where an ionic bonds where you have a formal positive charge and a formal negative charge. They are partial, so you have slightly positive charge here and a slightly negative charge there. This bond is called dipole. It has two poles, a positive and negative charge. Okay. We represent it by this little delta. Okay. So you see that hydrogen has a, if you look at the hydrogen, it has a 2 on the electronegativity scale. Chlorine has close to fluorine. Chlorine is very close to fluorine, so you know it's more electronegative. Both of these are nonpolar, so they share, but chlorine takes the electrons most of the time. So if you look at the electron density around chlorine is going to be greater than that of hydrogen. Both of them has a probability of finding hydrogen around the hydrogen, both of them has a probability of finding an electron around either the hydrogen or the chlorine, but you can see that for the majority of the time, you find a higher probability density in chlorine. Okay. This table is from a different book, still in chapter 8, that just looks at the dipole moment. We're not really going to cover this. You're not expected to calculate it, but basically dipole moment just says that there is a change in polarity. Another way of measuring change in polarity. I would review it because it might be on the final exam, but this will not be expected for exams in class. You are expected to know this difference. So you should know the differences will change the type of bond. So if you have a small difference in electronegativity, you have a nonpolar. If you have a larger change in negativity, then it's polar. If you have a very great change where you have formal charges, it's called ionic. So pay attention not only to what you have, or not only your electronegativity, but make sure you can identify whether it's a molecular compound or ionic compound. Okay, so in the case of polar and nonpolar covalent bonds, nonpolar has you can see that there is an electron density that is similar between the two elements. Okay, polar, there is a slightly greater chance of finding an electron in one location or the other. And then ionic, there is almost a great distance. You might even see this as two different circles individual, but you can see that the electron density is much greater in fluorine than in lithium. It's ionic. You have two different ions. So this concludes the material for Chapter 8. We'll pick up on Chapter 9 on Monday. We'll review the bond polarity because that will tie into what we're doing in Chapter 9. Be able to draw Lewis structures. Tell me what kind of bonds are polar and nonpolar. There will be practices. Please pay attention to the practice on Sapling. So Sapling has a training video where you can, or training homework where you can practice drawing things in Lewis structures. So make sure you do that before you actually do the homework in case there's issues with that. Chapter 9 is very visual, so yay. But if you do not understand the material in Chapter 8, you're going to really struggle in Chapter 9. Okay, so Chapter 8 and 9 are very intertwined. So make sure you practice counting valence electrons and drawing Lewis structures, because that is necessary for Chapter 9. Don't forget to do your video quizzes. This will count as class participation points, more so than your click for questions. So if you have any questions, feel free to email me.